So let's go over this work called Learning the Graphical Structure of Electronic Health Records with Graph Convolutional Transformer. This work is a novel attempt in order to understand the structure in the electronic health records and try to utilize that to improve the performance. Let's go over the abstract first. So the motivation for this work is clear. So different studies have shown the effectiveness of EHR data in activating different AI-based solutions to various problems. So a recent study showed that using graphical structure underlying EHR data relationship, for example, the relationship between the diagnosis and treatments improves the performance of prediction tasks. And based on these, they attempt to kind of tackle the problem of utilizing the structure and making the predictions. So how can we do better than just treating EHR data as a flat structured bag of features? The contribution of this work is essentially studying the possibility of jointly learning, performing supervised learning tasks, as well as learning the structure that can enhance it. So they propose different methodologies based on graph convolutional neural networks and transformers, and then they combine them in the graph convolutional transformer and basically investigate the performance of these models on various tasks that they have defined. So let's go over the introduction of this work. So EHR systems have enabled deep learning methodologies and have resulted in impressive performance in diverse tasks such as, so this part is important because it kind of goes over some of the main tasks associated with electronic health records. Predicting diagnosis, learning medical concept representations, and making interpretable predictions. So these are very important. So the common approach for processing EHR data with neural networks was to basically use a bag of features approach and kind of ignore the structures because, structures in the electronic health records is not really straightforward to understand. So usually the attempts to utilize electronic health records ignore that. So for example, if we consider something like this figure, the importance of structure will show itself. Like if we consider a timeline of a patient and we have t-1 visit, tth visit, and t+1 visit, if we consider this visit, we can say that, for example, this bill here, acetaminophen, is associated with cough and not abdominal pain or chest pain. So this is one of the instances in which some sort of prior knowledge on the structure of the different features might be helpful in final predictions. There were previous works such as mine by the same authors that tried to kind of outperform the bag of features approach in different tasks. But mostly EHR data do not contain structural information. But the question here is that can we also attempt to learn the structural information and kind of do that for enhancing the final performance? To address this question, they have proposed graph convolutional based pipelines, and they also proposed baseline pipelines and investigated the different experiments with them. So to sum it all up, the contributions of this work are: first, the novel objective of jointly learning the structure, the hidden structure in the electronic health records, and the supervised prediction tasks. And the novel modification to the transformer, because the previous works, as we will go over the related works, just use the transformer as a substitute for recurrent neural networks. In this work, they try to kind of utilize the transformer and kind of attempt to combine it with some prior knowledge as well in order to enhance the classification. And they show that unguided self-attention alone cannot properly learn the hidden EHR structure. So graph convolutional transformer is the model that they propose, and it's actually going to outperform all the different models in almost all of the tasks, indicating that it's a very good architecture for learning EHRs. So going over the related works. The graphical nature of EHRs have not been fully explored yet, and mine demonstrated that structure is very important. Mine was the previous work on this and was done on an exclusive dataset. Some of the recent works have focused on the connections between the transformer self-attention and graph networks, and these works, such as the graph attention networks and basically trying to kind of use self-attention to learn and capture non-local dependencies in images were the works that inspired this work. Now let's go over the method and the methodology of this case. So they try to kind of represent electronic health records as graphs. So that's the model for representing these. So for each visit, they have these notes, and these notes are going to be the visit note, a set of notes corresponding to diagnosis, treatments, and lab readings. One assumption that they have that could be considered sort of a limitation to this work is they basically assume that all of these notes can be mapped to the same latent space, and they basically denote each one of these notes as CI. So we have C1, C2, T until the last C, corresponding to all of these notes here. So since they focus on a single encounter, we omit the time index, so they consider each visit separately, and they have the features, and get it here, and they bucketize the continuous values of RI, which were the lab readings. So they basically have discrete values for those. And they use CI as the collective term to refer to a diagnosis, treatment, or lab reading, or a visit note. Now let's go over why structure is important. Even if we do not have any sort of information on A, there are things that can be done. So one thing is basically using a feed-forward neural network, and basically they can sum all of the node representations and project them to the latent space. But this is not good because the decisions that physicians have made will be somehow ignored. So one way to view this problem is to assume that all of the nodes CIs are implicitly fully connected. So they can assume that every edge between any two nodes could be possible. This is not a perfect assumption, and as we will see throughout reading this paper, they will try to kind of enhance this assumption. But yeah, one thing that we can do if we have all of these nodes, we can assume that all of them are connected and then try to learn which one of them are actually connected. So let's go over the different cases and the proposed methodology. So first, we have the graph convolutional neural network. So for the graph convolutional network, we should know what the structure is. So assuming that we know what the structure is, so we have the adjacency matrix A, we have this formula for computing the next set of representations for nodes. So assuming here that C j-1 is a matrix in which the rows are the representations of these C1, C2 till the end. We have Wj, which is the learned parameters for that layer. It will be used to map these to certain auxiliary outputs, and then we use this new A tilde, which is the summation of the adjacency matrix plus the identity matrix, and we have the diagonal node degree matrix in order to kind of average over the representations of one single node and its neighbors, in order to kind of let the information flow through these edges. We can use this as a structure and generate these representations, and therefore this would be the graph convolutional networks. Assume now that we do not know anything about the architecture, about the structure, so we do not have any information on A. So in this case, they propose the use of transformers. And the use of transformers is that we do not know what are the connections between the features, so we assume that they can attend to each other, and that they use the notion of self-attention, and they take these representations here for the past layer on each node, and then they have these trainable parameters to map them into queries, keys, and values. These attention weights then will be used with the values in order to kind of generate this auxiliary representation, and then they will pass it through the neural network to get the outputs. Now their main contribution is something called graph convolutional transformer, which basically proposes the use of transformer with some sort of a prior knowledge, making it easier for the system to proceed. This stems from the fact, as they mention in the paper as we go forward, is that in their initial testings, they showed that if they use transformer in the initial layers, the attention weights are almost uniformly distributed. And it is not good in the sense that there usually is a structure, specifically for the synthetic dataset that they have, there is a structure that is enforced. But what they show is that the transformer doesn't have a clear idea how to do these things, so they want to basically guide it. And the way they do that is that they go over the conditional probabilities and then they generate that, and then they use that as an approximation of how the adjacency matrix should look like, and then basically they take it from there. So if, for example, one goes over the dataset, they can realize that the probability of observing the EKG observation given that chest pain is observed is way more than EKG given that fever is observed. And that obviously comes from the intuitive connection between the electrocardiogram and heart and cardiovascular diseases. So what we can see is that statistically analyzing these connections would be important. So they go over the conditional probabilities between treatments and diagnosis and lab reports. And what they do is that they create this P matrix here, which is of this space. And they also enforce certain masks. So they know, for example, some diagnoses and some treatments should not be interconnected. So what they do is that they add this mask, and since the attentions are going through the softmax, they can add negative infinity here, and then they basically enforce that attention rate to be 0 for specific interconnections. So they use this as some sort of prior knowledge. So they have these masks here, and what they do is that for the first layer here, they use this P matrix as a substitute for A tilde, and they generate these representations, then go to the other layers, and from the other layers they use these definition of adjacency matrix, and then they use that. And then motivated by trust region policy optimization, they have these regularizations as well, assuming that attention weights are also sort of like probability distributions. They do not want to encourage diverging they do not want to encourage the divergence of these as we progress through the layers. So they have these different regularization terms. And then they go over the experiments. So they have the synthetic encounter record, and we have these. So let's go over the experiments and let's go over what they had. So they have this synthetic data set that they created, because in the publicly available EHR datasets there's no structure, so they wanted to kind of understand what happens if we do know the structure, and they basically create their own pseudo EHR dataset. So each level was generated conditioned on the previous level in a top-down approach, modeled with the Pareto distribution, and followed the power law that best captures the long-tailed nature of medical codes. And for the real-world dataset, they used the EICU collaborative research dataset. And one thing that is important here is that for the real-world application, because they wanted to treat the visits independently, what they did is that first of all they filtered out all of the cases in which they lasted more than 24 hours. So they took 1 day, and since these are ICU stays, same medications are probable to be applied more than once, so they removed the duplicates, and then they basically went over generating train set and test and validation sets. For the prediction tasks, they had multiple tasks. So the first two are defined on the synthetic dataset alone, and these are graph reconstruction and diagnosis treatment. So we can go over the table here, and one thing that we can see is that for the case of graph reconstruction, which is the case that we have a structure and we want to kind of guess what the structure is, if we have a GCN, we know the structure, so it's done. And for the diagnosis treatment classification is done as well. So the task for the diagnosis treatment classification is that we have diagnosis D1 and D2 and treatment code M1, and we want to assign 1 if there exists a D1 M1 connection, and 2 if it contains a D2 M1 connection. So it's going to be again a multi-label prediction. What they show here is these different baselines and their methodology. So let's go over what these baselines are first and the tasks. So the other tasks are mask diagnosis code prediction. So this is similar to what they do in the BERT training. And what they do is that they randomly mask one of the diagnosis codes, and then they try to kind of guess what it was, predict what it was. For the readmission prediction is the chance of readmission after this admission. So going over the EICU dataset, which is a EHR dataset publicly available over 200,000 patients, the tasks would be a binary classification and the data is available, and the mortality prediction the same way. For the baseline methodologies, they have the graph convolutional neural network that we talked about. GCNP is similar to GCN, but we do not have the structure for this. So they assume that the conditional probability matrix can be used instead. GCN random is the case that they randomly generate an adjacency matrix. So this is for the case of saying, okay, is randomly attending to other features better than not attending to anything at all? And shallow and deep are basically just representing all the nodes and basically performing a summation or something similar to the dynamic averaging networks on top of them to kind of generate the final representation. And deep would be shallow but with more layers. So for the graphic construction and the diagnosis treatment classification, what we did is that we have all of these and they show interesting results. One interesting result that we will see here is if we consider this GCN random, we can see that for the task of graph reconstruction, it outperforms the shallow, which means that for this task, randomly attending to other features have helped. And for the diagnosis treatment classification, in which the interconnections are seemingly are more important, we can see that the shallow outperforms the GCN. And we can also see that the graph convolutional transformer outperforms everything else in all cases. When we go over the other tasks, for example, for the mass diagnosis, we can see that GCT again outperforms everything else, and we can have some sort of comparison over the other things. And for the cases of readmission and mortality, we also observe the same thing. So GCT is a very good architecture, one could say. The KL divergences based on and also the entropies are important in basically figuring out where we are. One thing about the entropy is it should be mentioned because we do not want the things to be uniform, thus reducing the KL divergence, because we want the KL divergence to be an indication of how far the distributions are from each other while they are not uniform. And we can basically show them here, and it basically, going over the values, we can see that GCT performs kind of like an optimized and improved version of GCNP, and it's better than the transformer. And the last part of this paper is going over the attention behavior visualization, in which, for example, we can have a self-attention block 2 here. The red bars indicate that there exists a connection. These are ground truths. The blue bars are the attention weights, and the purple is the overlap of these two. For example, we can see that the attentions here are very well and properly adjusted. And this sums up this paper, which we're basically learning the structure of various features in understanding electronic health records.